to it. As long as people can hear me and people are happy, I won't put the microphone on. So if people can hear me at the back, I'll keep going. I started with BAS, as you say, a long while ago. I haven't really much experience outside of BAS, but I've got quite a broad experience within the organisation. So hopefully I can give you an overview, and if you've got questions at the end, I'll cover them then, and it can be on anything that you want. It doesn't have to be on aircraft operations. Thank you very much for the invite to come and talk to you. It is we are funded by the taxpayer and the government, so part of our remit is to come and speak to people. It is part of the role, really, is to get the science back out to the community, back out to the public, of what we are really doing out in Antarctica and how it's relevant for, the UK public. So I'll make my first apology. This is the only penguin shot you'll get. So if you hear a penguin, make the most of it, because this is the only one. That's an emperor penguin. Okay. So really, this was a sequence of footage. That's a Twin Otter. It was taken a couple of years ago by the BBC in part of their Frozen Planet programme, so I don't think they actually use it yet. But this, for me, this is sea ice. This is annual sea ice in here. That's obviously open water, and this is part of an ice shelf. This ice shelf is about 100 miles from Rothera, and you can see it's starting to break up. And this is a relatively small area, but for me it brings home the sort of scale of where we're working and the remoteness of where we're working. So, yeah, it really is starting to break up. It's broken up in the past, but it's happening perhaps quicker than in the past. So the region I'm talking about, BAS tends to concentrate historically in the past on British Antarctic territory. There is a treaty system which has put it in abeyance, but really that's why our bases are congregated and concentrated in this area. That's the sector of the Antarctic that politically UK claim. So access to the Antarctic, we used to be based from the Falkland Islands historically. That was really because it used to be by ship, and we used to come in from there. When we started to use aircraft, again we still accessed it through the Falklands, Montevideo, then through the Falklands. More recently we've been using Punta Arenas in Chile, and that has quite a number of benefits really for the organisation. The main runway is here at Rothera. It used to be a skiway, but we've now got a 900-metre gravel runway, and that's really the access point. It's an access point for a lot of other operators who operate in the Antarctic. So the American programme, the French, the Italians, the Germans, all come through with their Twin Otters, the contract aircraft. They all come through Rothera into the continent. Punta Arenas is about 800 nautical miles for us from Rothera. The Falklands is 900 nautical miles, and as the weather comes round this way, flying from there, you're actually flying into more of a headwind component, so it actually is better to fly from Punta, and it sounds like only 100 miles, but weather factors make it much better as well. There are other gravel runways on the peninsula. There's one on King George Island, and there's one on Marambio over here. They're much further north than Rothera, and they tend to cop all the low pressure systems that pass through, so when Rothera's got reasonable weather, they will be in 1,200 feet of cloud and clag, really. So it is ideal. Most people don't use these runways up here. Obviously the national programmes for those people do, but most people do use Rothera to access the rest of the continent. So we have these other bases up here. Bird Island winters, and that winters with 3, maybe 4 people, and goes up to maybe 10 in the summer. We run King Edward Point for South Georgia Government, and that's really, we do fishery science there, but it's on behalf of South Georgia Government. And there's about 10 people there in winter. Sydney Island has come to summer only, and all these stations up here are biological research. So Bird Island concentrates on seals, penguins and albatrosses. Sydney Island is a summer-only research station. We used to concentrate on lakes and things like that, but they do also do some bird research on penguins and sort of flying birds. When we come to Rothera, we do biology. We've got a marine programme. It's a wintering station, but like I said, it's one of our bigger stations. About 120 people are there in the summer, and it falls to 20 in winter. And the biological sciences are there with marine science, diving, upper atmosphere, things like that. So the whole gamut of science. But really acts as a hub for the access for UK science to the rest of the continent. Halley Station, another wintering station. at about 12 people in winter, 12 to 15 people in winter, and about 60 people in summer. We've currently got a build team there, so there's 80 people, but the idea is it goes down to between 50 and 60. So, relatively, high numbers of staff on station. These stations are quite small, and these ones here are summer only, so they're really fuel stops for the aircraft accessing the rest of the continent. So, yeah, the two stations I'm going to talk about are really Halley and Rothera, because that's where we do most of our aircraft operations. So, who are we? I've already said we're funded by the government. We get about £45 million a year to run these stations in Antarctica, 2 research ships, 4 Twin Otters, and a -7. So, that's who we are, and that's what we do. We do science. A lot of other countries have military presences in the Antarctic, but we're actually paid to do the science. That's why we're there. There is a political angle to it, but if you speak to anybody who's down there, they're down there for the science, not the politics. We are funded through the government through a body called Natural Environment Research Council, and that's our parent body, and they also own BGS, if you like, and CEH, Centre for Ecology and Hydrology, who release all the flood information. So we are under the National Environment Research Council umbrella. Why do we do it? We do it because we're paid to do the science, and it is a relatively cheap way for the UK government to keep its presence in Antarctica. So, mission. From the mission here, you can all read that. Obviously, the primary goal is science, but in our mission statement that the government sets us and we set ourselves, there is this political angle. And although that's put on hold at the moment, there is a political, arm to our presence and being there. We're regulated. The reason we're regulated is I'm talking about the air operation here. We're regulated by the UK CAA under an organisation called ASI, but that's driven through the Governor of the Falkland Islands. Our aircraft are registered in the Falklands, again, so are our ships, and again, that's historical, part of a political angle to the organisation. But we are governed and tightly regulated. It's an overseas territory. We're on the VP Foxtrot register, and we're governed by the Overseas Territories ANO. So there's an ANO for UK, a navigation order for all the flying and regulations, and there is one for the Overseas Territories, of which we're part. So that's how we're regulated. We're also regulated by the Antarctic Treaty, and the UK has ratified that legislation in 2001, and it's going through Parliament again. Neil Carmichael's driving through another private members bill, and it should go through this year to ratify again sort of this treaty legislation, international legal law. So outline costs, I do like this slide because the aircraft are funded here, 5 aircraft in here, and our ships, there are only 2 of them are funded here, so we always have to hammer that home to the marine fish heads. So we fly about 450 hours a year with the -7, primarily between the South American continent and Antarctica, and that's bringing people in. And it changed Bass's operation massively because we were suddenly able to do short periods in Antarctica, and that enabled us to attract different sort of set of people from universities and other places to come and work with us, rather than spending 4 months, away from wherever you were having to leave behind. So, professionally, people weren't willing to do that. So it did allow us to attract a different group of people. Twin Otters, I've split this between sort of science and logistics. Science is both the science sort of as platforms, it's also the science of delivering science for projects, delivering equipment for projects. But the logistics portion is opening up depots, these summer-only fuel depots I was talking about, and purely moving fuel in the continent to support the fuel that's happening. So there's quite a portion of it is just the logistics of the science in Antarctica. So a total of about 1,800 hours a year. So a bit of the history. The first flights I know of in Antarctica were in about 1902, and it was on Scott's Discovery expedition. So he was there from 1901 to 1904. So they were used right at the start of exploration, and again it was to prospect sort of routes in the continent and things like that. And it was a hot air balloon. So, you know, that was when it started. We then had Wilkins, who took a float plane and was flying around Deception Island, which is on the Northern Peninsula. And then, of course, we had Admiral Byrd from the American program flying over South Pole. I think that was 1929. Yeah, in 1929. Bass started air operations, and most of it was float planes, things like that, although there was a skied Oster down there. I think it was an Oster 5. And that was in 1946. And the tale of aviation early on in the period is quite a classic. You know, they take aircraft down them, and basically if they don't bring them back, the reason they're left there is that they were broken, or either by mechanical failure, or they were broken on landings or takeoffs. And it wasn't until sort of really the mid-late 50s that, you know, planes lasted much more than, you know, a couple of seasons. But, you know, imagine flying something like this in, you know, the weather conditions, you know, where you've got, you know, 50, 60 knot winds, things like that on the continent. It's very different flying that sort of machine to a Twin Otter or a Dash 7. So, yeah, so, I mean, the first, this Oster that they first took down there, the guys actually crashed had a heavy landing, and actually were on the peninsula, and they used the auxiliary fuel tank as a sledge, and they had to sledge to the coastline. It took them 6 days to go about 28 miles, I think it was, and then they were picked up at the coast by a Norseman that was down there at the time. This is a Norseman, again float plane. Again, this was used by the sort of early organisation that then became British Antarctic Survey. So there is a rumour that that was one of our directors, but it's not true. We moved on to turbines then. So all these earlier aircraft, not only were they quite lightweight and small, they were, you know, piston engined. The move to turbines brought much greater reliability, a bit more power. You can see there's a complete dog team here, and yes, they do get them in the aircraft and they do fight, but as soon as you start taking off, the sort of unusual atmosphere for the dogs made them all calm down and sort of cower. So as soon as the pilot throttled up, they would all go quite quiet. But yeah, the single otter was really the start of the turbine era. And by 1969, we've moved on to Twin Otters, which really changed the operation quite significantly. So that's a Twin Otter flying over a bit of the peninsula that's just, I guess, about 100 miles from Rothera. So what do we do with the aircraft? There are really four main reasons we've got them. Obviously, we do sort of science support, logistics on the continent. We get people to the continent, but we also actually use them as science platforms themselves. Two of the aircraft are modified significantly for science. There's no search and rescue provision down there. You are your own search and rescue, and also you're also sort of other nations search and rescue. It's a very integrated community, if you like, of support. So the American program, I mean, this morning I did hear that they've got a missing aircraft between Pole and Terra Nova. I haven't heard anything else from Bass directly on it, but certainly an EPIRB was going off and they've got a missing aircraft. So there were 3 crew on board, but hopefully they've landed. The reason they couldn't launched a C-130 to look at the point the EPIRB was giving, but the wind and weather conditions were so poor they couldn't see anybody, anything on the ground. So we're waiting to hear about the sort of where that develops. But so you are your own SAR facility, and if we're called in to help with that program, we will drop everything and help with the program. Medivacs, we have at least one a year, often within our own organisation, but the German program we've medevac people for. You normally have broken things, often recreation. The last 2 injuries that I know of were recreational skiing. So we have a 24-hour duty of care for people. So when you're in Antarctica, you can't just expect people to sit reading a book or watching a video. The type of people we recruit are active people interested in getting out. So we've got to accept that if they're playing 5-side football on the apron, there is a risk they'll hurt themselves, and they do. We've got 4 Twin Otters. The biggest difference between one that you might fly with Scilly Skybus to Scilly Isles is we've got an STC for £14,000 operation. So normally they're £12,500. We've got a maximum takeoff weight, sort of STC, to 14. And that makes a big difference because the distances we're flying are greater probably than you would intend to fly in the UK and other sort of places where they're designed. But also this adds about £700 to your takeoff weight, just the fact you've got skis on. These are wheel skis. You can get board skis for the aircraft, which are a bit lighter. They're not massively lighter, but we tend to operate in and out of Rothera. So even, it isn't really even worth us changing to these board skis when we're operating in the continent, because it's a bit of a faff. And yeah, we're going to need boards when we come back to Rothera anyway. Wheel skis when we come back to Rothera. The other big difference is the distances we're flying means we need a reasonable amount of fuel. So instead of having 19 people that you fly to the Scillies with, we've only got 6 on board. So we've got a pilot and 5 others as a maximum. There's quite a lot of safety equipment in the aircraft, survival equipment, stuff like that, tent, different things. But the other thing, we also fly, even if you were flying fuel drums, you would fly with a second person on the aircraft. The aircraft's single pilot, but we always fly with somebody else, because if you can, you're going to be cooking in a tent, and one of the big risks for us is carbon monoxide poisoning. So we always have a buddy system where you look after each other. And it would also apply if if you have to erect the tent and stuff like that and it's windy, it's very difficult to do it on your own. So we always fly everywhere with 2. If you talk to people in the organisation, they often say, I'm off on a co-pilot flight. Really, they mean they're off on a pilot's assistant trip, because although you sit in the right-hand seat, the pilot might let you use the controls, but really you're there and to help load the aircraft and stuff. But it is on a rota basis, so it is a task that people have to do on a rota, same as the washing up and things like that. So that's treated as quite a big perk. So Rothera Station, I talked about this being our main base. You can see the tracks up here to our skiway. Here's the hangar. This is 900 metres long, so the hangar takes the Dash 7 and 3 Twin Otters, so we can't get the 4th Twin Otter in. And these are the fuel tanks here, 250 metres cube of fuel in each. 3 of them, the 3 on the far side are for the station, and the 3 on this side are aviation fuel for the aircraft operations. And we usually use 2 of the tanks every year. So we get refueled by our own ships at the start and end of season, and maybe even a top-up from another operator's ship. So the Germans have topped our fuel up, the Americans help top the fuel up. And this is on an exchange basis, because they've come through to access the continent and used our fuel. Part of the quid pro quo is they replace it, and we can't get all the fuel in ourselves, so they will use their assets to get the fuel in for us. So Rothera, I talked about the runway. We also have a skiway up here, and this is where it used to be operated from. The skiway is about 3 kilometres long, 2.7 kilometres long, and you access it through there's a dip in that ridge line here, skiway col, it's inventively called. And you come through skiway column to the skiway. But the biggest thing from a pilot's perspective is you can just see probably that faint line there, which is the track of skidoos and snowcats onto along the traverse and onto the skiway area. But up here you can't see any detail at all, and it's just because of this small bank of cloud. It cuts down contrast and horizontal definition is what we call it, but basically the ability to see a horizon. Because there's this ridge here, but there's one that's twice the height tucked away in here. And this is a massive implication for pilots. Although it might be, cab okay, if you've got altostratus at 10,000 feet, it cuts down this contrast. People who ski will be familiar with sort of the poor contrast conditions. But it has massive implications for us when we're flying, because once you've lost the sight of the surface and can't tell depth perception, you're really in a big problem as a pilot. So that's probably one of the biggest. There's obviously a windy continent, a cold continent, but in pilot terms, this lack of horizontal definition and contrast is probably the biggest limiting factor to some of our operations. So this is inside the hangar. There's certainly people in the audience who are familiar with this, having spent time at Rothera. But we've got the Dash 7 here and the Twin Otter. They're both on check. They're sort of manoeuvred around in a different way to get all 3 Twin Otters in behind it. It's not a heated hangar. It is insulated, so if it's minus 15 outside, it's probably only minus 7 or 8 inside. But likewise, if it's plus 6 outside, which is unusual, but it does happen, it's probably only around freezing inside. Hence, the doors will be open on days like that. So it has its benefits having an insulated hangar, but it's just not practical to heat it. Halley Station I was talking about. This is actually on a floating ice shelf. You saw it at the edge of the Weddell Sea. The ice shelf that it's on is moving parallel with the coastline, and it moves at about, I think it's moving something like 1 metre a day along the coast. So, you're moving sort of half a kilometre nearly a year. but it's also going up and down with the tide, 2 metres, and we've got a skiway there, so yeah. This is the new station, this is the artist's impression, but I'm told it looks scarily similar. It looks like something out of a sci-fi movie. It's sort of glass reinforced plastic, sort of skin, built around a steel frame structure. And these legs lift up and down hydraulically, and they can put snow underneath it, because you've got 2 metres of accumulation of snow here every year. So you even, if the old building was on jackable stilts, this building you can raise the legs and put snow underneath it and keep it above the surface. But the reason it's on skis is because I said it was moving down the coast. Now they think when Shackleton passed those ice cliffs on his expedition that failed and they ended up on the boat going to South Georgia, that they think that he passed, from the position reports he gave in his log, they think that the ice shelf was broken back further than our station is, or was, on stilts. So that's the reason why this new station was built. It was built sort of 20 kilometres in from where our original station was. And the ability of this is, it's travelling parallel with the coast, beyond the breakout line. What we do is we just disconnect modules and tow it back to the original starting position, or close to where you were starting. So, in theory, this base has got a much longer life than the 15 or 20 years that typically our other stations have had. So, I talked about some of our operational area. Most of these legs are about a Twin Otters worth distance, about 240 miles is commonly the frequency of those legs. The little crosses are fuel depots or scientific sites we're going to. And I mentioned, if you fly in a Twin Otter, you'll refuel at Fossil Bluff, you'll refuel at Sky Blue, and then maybe you'll make some of these sites further in the field, but you'll probably refuel at them as well. So fuel is key to our process. But the Twin Otter's quite slow, really. It flies at 135 knots, which is much slower than you would expect an aircraft, and that's mainly due to the skis. Without skis, it's about 150 knots. But it's still a long way. If you think, if we put Rothera at London, just a normal day's, flying with Sky Blue, it's a milk run. It's not anything, spectacular. And, it's the equivalent of flying, out to Munich. Some of our other operational area, going to Halley, would be the equivalent going past, deep into Poland. So we do end up going quite protracted distances in something that only does 135 knots. And that's really, part of the reason you carry so much fuel, is these distances are large. The sort of extended area, if we take where we work with other countries will provide us with the fuel and stuff like that. If we take that, then this is the footprint of our current operational area, and that's in the Twin Otter. So yeah, we are doing big distances, in support of UK science every year to cover this. But I think you get blasé when you work on the continent about the distances that people are going and the distances that people are travelling here. When they say, "Oh, we're off out to download the LPMs," and they might be out in this area here, and they may be gone for 2.5 weeks, 3 weeks to do that piece of work. So this is really the Twin Otter in its right element. You see the skis are down. It's got huge flaps, and they're associated with the ailerons as well at the extent of the far end of the wing. Unfortunately, the sound isn't playing, but one of the big things is obviously there are no brakes. So when there are slopes involved in landing in the field, the pilot has to take that into account quite a lot. But with there being no brakes, the problem is if you've left it for 5 or 6 hours, it's probably stuck to the snow and frozen in, so you have to dig it out. So it's not usually going to blow anywhere. We have tie downs for them, but normally getting it unstuck is the issue, not freeing it off. So that's the Twin Otter. And that was putting people into the field. So you'll put in about 1,800 pounds of kit on that 240-mile leg, which is, in some of the airframes, some of the lighter airframes, it will be 5 drums. In a couple of the heavier aircraft with the survey kit, we take the survey kit out, but with the fixtures for the survey kit, it's probably about 4 drums. So we put scientists in the field. This will be about 600 miles from Rothera. It's down near the Ellsworth Mountains, which are the sort of highest mountains in Antarctica. So mountain people go and climb Vinson is just off here. This ice stream is the Rockford ice stream. I always envisage ice flowing off Antarctica a bit like icing off a cake, and it would flow evenly off all the edges, but it doesn't. It's really focused in sort of 10 maybe 12 ice streams on the continent. And this focused flow is how most of the ice gets off the continent. This ice stream here, where these guys are camped, is probably moving at 700 or 800 metres a year downstream. The reason they put sort of these, it looks a bit like porcupine, is you should put a cane by everything you put on the ground because it's going to disappear if it snows overnight. So, yeah, they flagged everything around their camp. And these tents are a bit, you know, they're still cotton ventile tents. They have a nylon inner, but there'll be 2 people in each tent. Like I said, we don't camp on our own. So there's 4 people at this site. And this is the camp, and there's camps there, and there's also this fuel depot that we established for a piece of work there. This track here is a skidoo track, another skidoo track coming down here, so where they're going out to different field sites for their work. But these lines up here are the reason why I was talking about it has to be very, very good contrast for a first landing anywhere you go. Once you've got your field party in, they can put flags in or beast with a skidoo, a skiway for you. But the first ever landings are always done with clear, bright sunshine on the surface. And the reason is these are crevasses, and these are absolute monsters that weren't predicted to be there because this is a flat area. You know, normally you'd expect crevasses on something that's convex, where the stress is opening them up. So yeah, we've got, you know, this chap here. You have got monster crevasses, so you know you do have to be careful. The procedure for any aircraft landing in somewhere new would be to trail skis. So they would fly along probably at sort of 50 to 60 knots and trail skis with some weight on the undercarriage, so that in theory it breaks these bridges down, and you then take off, fly back around, inspect your tracks, and then you land in your tracks. So this was the depot I was talking about. When I talk about getting 4, maybe, well, at the distance this depot was from Sky Blue, it's 4 drums a time into the depot. There's 200 drums there. There's about £47,000 of equipment on top. It took us over 4 years to get this depot on the site with all the science kit. I talked about it moving towards the sea, 700 metres, 800 metres a year. Consequently, you flag it and put drums up. Now, we went through a trial process where we thought, well, these yacht radar reflectors must be quite good kit. So we took them out and trialled them. But they didn't work as well as empty drums that we'd historically used as depot markers. And maybe, I think maybe it was because with it being a round surface, you must get quite a good reflection all the time from one surface, whereas with the radar markers, perhaps in some angles you don't get the reception. So on the weather radars, they have a search facility, and these show up absolutely brilliantly. Some depots have got more snow than others. We go around them. This is a science and fuel depot. Some depots are just fuel only. And this is a picture of the aircraft's landed. This is a fuel only depot, and that's the drum. So yeah, the pilot and co-pilot are going to have a reasonable amount of digging before they refuel that aircraft. So, obviously being a pilot with bats is obviously very glamorous. So Dash 7, we only have one of these, and it is pretty unique. It's been modified with a massive cargo door. Again, the sort of takeoff weight's been uprated to £47,000, and because we're not doing sort of intercity hops like it was designed for in Europe, flying between, say, London City and Paris, there is a capability for fuel tanks in the wing here. So the normal fuel tanks are here, but we've got AUX tanks in the wing, and they've got the same capacity as the main tank. So we can, fill it right to the max, and then, fly wherever you want, but you then don't have any payload. But yeah, it's a fantastic aircraft. It's got about 11-hour endurance as its maximum, and I'll come on to that in a minute because that gives it a huge sort of surveying capacity, and we're about to start to use that. Both the Twin Otter and the Dash 7 are short takeoff aircraft, but you can see the depth of that wing. It's pretty slow. We're talking 250 knots on a good day. So yeah, from South America to Rothera is about 4.5 hours. With no significant headwinds. We improved the pilot's sort of environment really. The instruments were reasonably old. They weren't particularly unreliable, but really the biggest factor for us upgrading the pilot's cockpit in the Dash 7, we have plans to do it in the Twin Otters and we're bidding for money for it, but we haven't done it yet. But the biggest thing is situational awareness for the pilot. He's in a quite difficult environment anyway. It can get quite busy, and displaying this information more simply was quite a key factor for the environment we were in. So this was the start of the project. This is what they had originally. This is the wiring. You start to really worry when it's in that state. There's about 7 kilometres of wires that went into the nose, and then it was easier to operate instead of working through the hell hole in the undercarriage. Working, with the nose off was the way to go, so it was de-riveted and taken off the aircraft. And what we got in was 2 EFIS screens on each side, so we can display, GPS data. We can give them the TORS information, weather radar information, whatever they want really can all be called up, and the charts and things. So for when we're working sort of on our ferry flights. So yeah, it made a massive improvement to the pilot sort of environment. This is its standby instruments here, and these are the radio consoles that have changed as well. So it's more reliable, but the biggest reason for us really was the safety factor and situational awareness. So current operation for the Dash 7, it really is passenger transfer, but we do use it to that blue ice runway that we've got at Sky Blue, and that really short circuits our logistics chain. So another good reason for not going by ship really. We fly from Rothera and it takes 4.5 hours. On the ship it can take you up to a month if the sea ice isn't right, and another good reason. So this is what it would look like on the Dash 7. This is just maybe 10 miles east of Rothera. Normally you'd be there with 50 other passengers. Again, distances for flying things, we only fly with a maximum of 16 from Punta Arenas. Reasonable amount of safety kit covered in the aircraft. But yeah, who says turboprops aren't sexy? So the next clip is it landing at Rothera from the north over some ice cliffs. The performance of the Dash 7 isn't too different from the Twin Otter. So you're talking maybe sort of 300, 450 metres for takeoff, and about the same for landing. So this is landing in about the middle of the apron, so you're talking about a couple hundred metres into the runway, maybe 300 metres, and yeah, it's not very dramatic at all really when you're in the aircraft. Why did we like it? Really the stall factor. Our runway is only 900 metres long, and it's quite limited at the southern end because the water drops very deeply and steeply into sort of 600 metres. And at the northern end, we just couldn't really push it out any further. It's into 30-metre water already. So really, it was a runway limitation. But also, if you've got 4 engines, you're flying over a big cold piece of water for maybe 4 hours. And this is the perspective pilots have of the runway. So yeah, it is reasonably short. You've got the hangar up here with the fuel on either side. So yeah, this is it landing. Obviously it's got all the flaps, those big propellers. We've got reverse, obviously got the brakes, but it stops with no drama whatsoever in about 400, 450 meters. So I talked about the Dash 7. When you fly from Rothera, it probably takes you 2.5 hours to fly Rothera to Sky Blue. In a Twin Otter, that's going to take you maybe 4 hours, but you've got to stop and refuel at Fossil Bluff, and you've got to take on some fuel. So you're going to have to put that fuel back to Fossil Bluff when you next go. So Dash 7 will take 21 drums to Sky Blue, and the Twin Otter will have taken 4, but it will also have used maybe 5 at Fossil Bluff, which you then have to replace. So it massively short circuits the operation. We can get maybe 3 rotations in the Dash to Sky Blue in a day. You'll be taking 4 drums, and that's it. With a Twin Otter, and that will take you all day. So I use the example of drums there, but it could be science kit, anything you want really. That short circuit of our operation is taken for granted now, and we couldn't do without the Dash 7, both transporting people to Rothera, but also as part of the logistics chain. The Twin Otters would then shuffle it out to wherever it's needed from then. So this is back in the bad old days when we used to clear the runway by hand, the blue ice runway. It's now cleared by machinery, but yeah, the Dash 7 on approach. This is a big gun attack at the end of mountain that pokes out the ice sheet. The ice sheet at this point is about 4,500 feet thick, so you're at 4,500 feet. We were asked what was the coefficient of friction of the runway. I don't know. Depends on temperature and also the load-bearing capacity of it, but if anybody knows what 4,500 feet load-bearing capacity of ice is, we'll be interested to hear. So this is the runway down here. The reason that we've got blue ice there is scoured by the wind, hence it's quite windy there usually. We've got very low crosswind limitations on it, probably 10 knots is too much. And really, that's because you don't have any friction. You're relying on stopping the aircraft on the reverse you get on the propellers, and they control it with asymmetric reverse. We do have fixed facilities here. Not spectacularly comfortable, but at least it's not a tent, and it's got a heater in it. These are the guys. This is one of our glamorous pilots in his normal uniform of a boiler suit. These two mountaineers are looking after the depot. And this guy's a radio operator who's come from station to give these guys a hand, just because it's hard work. We probably move maybe 500, 600 drums through this site, refuelling our aircraft every year. So you're rolling them on off the aircraft, you're refueling the Twin Otters with them, or you're digging them out of the snow. So yeah, it's obviously a recent flight from Rothera. You've got bread and fresh fruit here, which is a bit of a luxury. But this is that 7 landing on that blue ice on a really good day. So it is spectacular. So you've seen the chart. I've discussed that already. Science platforms. The Twin Otters, the Dash 7 actually does also have a science capability of magnetometers and gravimeter, but I'll cover the advances and what we intend to do with the Dash in a minute. What I'm mostly going to talk about here is the Twin Otters. 2 of them have camera bays, camera hatches, so we can install hyperspectral instruments or photographic instruments within them. But although they're similar in that fact, one of them specialised in meteorological instrumentation. So we've got a turbulence boom out the front and a cloud probe, a particle probe on the wing. And we've also got an aerosol inlet on the other side and other different bits for met science. And this is it flying over the Romy ice shelf. And what they're interested in is the flux and the dynamics between the ocean, sea ice and the atmosphere. And we're talking about the boundary layer, so we're talking between sort of 30 and 50 metres. It's probably -20 here, so what you can see here is we call it sea smoke, and it's sort of the condensation coming off the relatively warm water into the cold atmosphere. And what they're looking at is the difference in radiation coming from above compared to what's being emitted by both the ocean and big pieces of pack ice that are forming. So this is called grease ice. It's sort of looks like a film on the water. So yeah, it's relatively bumpy. You can see the aircraft sort of bumping about in that sort of unstable, turbulent boundary layer. The other aircraft has got geophysics equipment on it. It's gravimeter inside, magnetometer booms on the end, and then this under here is VHF aerials. Now the gravimeter and the magnetometer, if you've got a nunatak, a mountain poking out, and you look at the signal from that in terms of its density and magnetic characteristics, they can extrapolate that under the ice and extrapolate the geology from those nunataks. This stuff here, old radals were VHF, and they used to suffer quite big errors when you flew over ice and snow because the VHF signal penetrated and then reflected from the base, so you would get quite big errors associated with radals. So changed frequencies nowadays, but we use this sort of artifact, if you like. We use this function for us to reflect off the base of the ice and tell us the difference and the depth of the ice. And you can also see if there's been a volcanic ash layer, you can see that reflecting the VHF signal off the base. One of the problems for us is this is quite high frequency. We'd like to use lower frequencies and perhaps tow antenna in the future, because warm ice has lenses of water in it, and the very high frequency stuff that we're using is interfered with by those water lenses that may be meters across. The longer the frequency you use, the more it misses those out, and you can see sort of warmer ice. And of course, warmer ice is the ice that's melting. So although we're looking on the continent at the moment at very cold ice, we'd like to extrapolate that and move that out further towards the edges of the continent, and also Greenland. So they're the details of the Twin Otter geophysics kit. But I really wanted to make some of this science real. I mean, these are the ice sheets on the peninsula itself. This is where the Twin Otter was flying over, just this little piece down here at the start of the sequence. But these ice shelves have collapsed in, really just a little more than the time I've been going to Antarctica. So, it is real. Now, they have collapsed in the past before, but one of the worries is that obviously they're floating, so when they collapse, they don't contribute to sea level change. They're floating already. What the worry is they act a bit like a cork and a bit like a moderator of flow of the ice off the continent. So if you remove the cork, you speed up the flow of ice off the continent. And I've already mentioned that this flow isn't even and if you remove the cork from some of these ice streams, you might significantly affect the ice flow of the continent in a disproportionate manner. So this is the geophysics Twin Otter. We worked with the American program to survey about 120,000 kilometres here and about 70,000 kilometres here. They had a survey aircraft and so did we. They put the fuel in. There were about 5 other nations, Japan, China, the German program, the Aussies and the Americans in this. Because obviously I was talking about the logistics of getting stuff to here. We just cannot do it on our own out here. And it is one of the good things really, is we do have this facility within the continent to work with other programs. They think this mountain range in here was the sort of seed, the catalyst for the original ice sheet forming in Antarctica. But one of the big areas of interest at the moment is this Pine Island region, and this drains that whole area here through one glacier here. They think the thinning of this ice sheet thinned about 40 metres in the last 10 years, and they think this alone has contributed about 0.3 millimetres every single year to sea level rise. And that's just this one glacier as one ice stream exit. So this is the American program, completely different to us. Instead of little Twin Otters, they have giant Hercs, dropping maybe 40 drums. But they'll drop these drums for us, we'll collect them up, and we'll use them. Thank you very much. They've also used these boys to drop us fuel at that same site. From Christchurch, they refueled at McMurdo, and then they drop 120 drums a go for us. So they put nearly 500 drums. They did 4 rotations and did nearly 500 drums for that survey I showed you, that 70,000 kilometre survey. So yeah, the Americans have it. It's good to have a sort of a big brother who can help you out when you need it. Also, that's some of the stuff on sea level rise and things. People also talk about global warming and carbon dioxide, things like that. This is just literally 15 kilometres from Halley. It's part of the ice sheet. These layers here, it's been shown that they are annual layers, and obviously as your 2 metres of snow up here gets compressed, it gradually compacts down and down and down. And eventually, up here, there is gaseous exchange in the snowpack. There's no doubt about it. And it probably takes about 40 years worth of compression before you get sealed ice, which is, define the bubbles and they can't transmit between each other. So yeah, you've got this undoubtedly annual layer here being laid down. We've drilled through it, other international programs that we've been part of have drilled through it, and really you get out these ice cores. So yeah, you drill down 2 metres at a time, you bring it back up. When you've gone sort of 800 metres, or I think the deepest ice core is something like over 2 kilometres, you're bringing up this 2 metres every year, every single time you pull it up and down. It's a hugely labour-intensive process. But when you get it back, you've got on the surface through it, you've got this ice, which is analysed chemically, and you can look for things like lead in it or other items. But you've actually, unusually, and instead of using markers like tree rings and stuff like that, we've actually got a sample of the air, albeit a fudge factor of about 40 years. But you've got a sample of air that was about at that time. If it was 100,000 years ago, you've got a sample of air that was 100,000 years old, plus or minus 40 years probably. So, what does it tell us? We don't actually go back. So this is the start. This is going back in time. The deepest ice core we've got out of Antarctica at the moment is about here. But from other indicators, and this is sediment cores, they can show that isotopically this is the temperature that was experienced. And you can see there is a bit of a difference here. There is a change in the cycle. We don't really know why there's a change in the cycle, but there is. But I mean, you can see it's pretty regular, and you can work it out. This is due really to the axis around the sun, the angle of tilt, and the wobble on the Earth's cycle around the sun. So there's 3 cycles to it, and that produces a difference in temperature of about 1 degree as your maximum difference in all these different things. But what happens is carbon dioxide is soluble in water, and it's really, really sensitive to that solubility coefficient, and there's a feedback loop. So as you raise the temperature, more carbon dioxide is released, which raises the temperature, so more carbon dioxide released. And the difference between a cold period in an ice age down here and a warm period is about 10 degrees, 9 or 10 degrees, and they can show that this feedback loop is what amplifies the orbit around the sun and that energy input to Earth. So this is the temperature, and the red line is carbon dioxide taken from these little cores. I said we couldn't go back to 1 million years, we've gone back to about 700,000 years, and this was a big French project, Dome C. We were part of it, but yeah, it was on the other side of the continent. Most people will agree, you know, these things are linked. But the biggest thing for us really is when we get to today and when we get into sort of modern times. And the next graph I show you is really an amplification of this corner. So if we look through here, and this is an amplification again, so this is sort of 150,000 years, but 1,000 years we break again. So they're pretty well linked, but I think for me the clincher is the rate of change, the fastest rate of change we've seen in the past is about 30 ppm over 1,000 years. What we're putting in here, the last 17 years have been 30 ppm. So naturally, these are the levels we've been seeing at least up to 800,000 million years ago. These are the levels that we would expect if you go back to the other graphs. That's about the normal maximum. And what we've done is we've taken it out of the normal range, if you like. And that feedback loop, if you work out the temperatures that you're going to be seeing, the lowest possible stabilisation back here, is really 50% more than you've seen in the past as a natural cycle. So I think the modellers and the sort of politicians will come to agreement, and I think we're going to end up in this region here in terms of stabilisation of CO2 in the atmosphere before it starts to decrease. But yeah, I mean, I don't think there's any denial that these two are linked. And the big thing for us is one of the reasons we're doing these surveys in Antarctica is we're looking for deeper ice cores because they go back further in time, and we can learn a bit more about the past really. And people say, how accurate are they? You can measure lead, and lead. Really it's a northern hemisphere thing. Certainly if you go back to 400 AD, you can see the Romans were starting smelting and stuff, and you can see that lead production in Roman times. You can see the peak associated with it, and you can see when they wrote in their records they were short of lead in their lead mines. You can see the dip. So you can see the cycle here. This is really lead from sort of the petrol engine starting up here. So you can see when it was banned in different places, the effect of the world wars, stuff like this. But you can see there's a massive change. Lead in petrol was banned in Brazil at first, and you can see, and that is reflected in the snowpack in Antarctica. One of the other gases that's detected in the 1950s, halethane, is a medical anaesthetic gas, and we can detect that in the air samples in the snow in Antarctica, and that's just used in hospitals. It's an artificial product. So these things are pretty sensitive. For BAS itself, we're changing quite a lot. There's much more pressure on us to use our resources more efficiently, and one of the things that's happening is our change of focus is moving from the Antarctic to the Arctic. Last year was the lowest sea ice minimum. It's good. The effects and changes that are happening up here, we're being driven much more to go and find out what's happening for UK science. So actually this summer we're working in Svalbard up here with the meteorological aircraft. The biggest real modification change that we're talking about, there's a lot of mods that are associated with our operational sort of environment, but the biggest one for us is this instrument port in the -7. We're putting a 1.6 metre by 0.6 metre hole in the -7, and that will enable us to put hyperspectral instruments in, put snow depth radars in, all sorts of things. And the big driver really is, this is the range of a Twin Otter, and this is the range of the -7 using normal airports. So you can see we've got about a 2-hour loiter time over the North Pole if they want to look at sea ice physics and things like that. So for us, the change in emphasis from logistics for the -7 to a dual role aircraft is massive. None of the tundra regions are out of the escape of us going and looking at them, and it will be a unique platform that no other country has. So yeah, we're hoping that it will provide a facility that isn't duplicated anywhere else. We've also in winter we've tried these small UAVs. There are applications for UAVs definitely. We don't see it particularly as competitive with the fixed wing piloted aircraft, they do totally different things for us, and it frees up more time for us to do science or whatever else we want to do with the aircraft if we can use these type of instruments to deploy sensors or go and measure things. And certainly in winter, we won't have fixed-wing aircraft with pilots down there, so this is the only option for us later in winter. So this is Twin Otter. This is what the pilots go for. This is, I think, what everybody goes for on their co-pilot flights. About 20 miles from Rothera. Rothera is in the Merc over here. So, but I still don't think we'd be still haven't got it quite sussed. And that's it. I'm quite happy to take questions.
Thank you very much, Rod.
Thank you for that. For the Twin Otters, particularly, and even the Dash 7, the service height ceilings of those aircraft are pretty low. 24,000, 25,000 feet. You're flying over some serious mountain ranges. And also you're having to fly through, I guess, extreme weathers. How do you cope with that? I mean, that's pretty dangerous stuff.
Yeah, the height, the sort of atmosphere bulges at the equator and stuff. So although the highest mountain in Antarctica, Vinson, is only 16,000 feet, the ISA doesn't really work so well. There are correction factors you have to add because it's worth about 2,000 feet, this bulge in the atmosphere. So yeah, your altimeters do have to be corrected, but most of the time we fly on radals. Once they start to get low to the ground, the pilots will be using the radal rather than the altimeter, because you've got no real means that, who's going to give you the local QFE? You're flying to somewhere that's 800 miles away, the QFE you got off the airfield is irrelevant. So we use pretty much radals. The mountains aren't that high. They are about, commonly your MSA, could be 14,000 feet. We have portable option on, packaging in the aircraft, so the pilots can use it. They don't tend to. We tend to sort of, fly at 12,000 as an absolute maximum. The Dash 7 obviously flies higher, but and the weather doesn't go so high. There isn't a thermal activity in the atmosphere to drive thunderstorms or anything like that. So your weather tends to be a bit lower. You can have cirrus clouds at 12,000 feet, 15,000 feet. So the continent can be 10,000 feet high in the middle, but above it, you're probably above the surface. You don't have the weather. So there isn't the thermally driven weather, but you do have drainage winds off the continent, katabatic winds, stuff like that. So we tend to avoid the weather. So if you're going to, forecasters play a huge role in our planning of our program, because if they say, there's a low pressure, and a low pressure can be 930 millibars coming around the continent, and if one of these is coming, we will move the aircraft back to Rothera. If they say it's going to meet some part of the peninsula, we will move the aircraft back to Rothera and tuck them in the hangar and wait till it's passed. And the same if you're in the field, we might bring the aircraft, which upsets the scientists. We might leave the scientists on the ground and say, we'll come back to you in 5 days. There's 80-mile-an-hour winds forecast. We'll bring the aircraft back to where the forecaster says, you'll be perfectly all right there. We'll wait there for a couple of days and we'll go back and get them. We have damaged the aircraft in wind shear events. One of the aircraft was damaged in the wind shear event, but that was in the 80s, I think. We have damaged an aircraft in crosswind landing at Rothera, but we've changed how our procedures. The pilots can go and use the skiway because it's a very localised effect. The forecasters can predict it reasonably well. So there are different things, but probably we run away from the weather would be the best description of how do we cope with it. We don't tend to get the thermal activity weather, and if it are these big cyclonic things coming, we'll move out of the way. So, does that answer your question?
Yes, it does. Thank you.
How do you get your the Twin Otters to the mainland? I presume you don't fly them from South America.
Yeah, we do. Yeah, we fit ferry tanks. So the aircraft themselves are serviced in the northern hemisphere. Back at the start, it was military guys would be seconded in. So when I first started with BAS, Remy would be seconded with 3 engineers to BAS, and they would look after the Twin Otters. When the Dash 7 came in, it was a bit too much for the REME guys, who really helicopter and islander-based experience, to work on the Dash 7. So we then started using private companies who had that ability, and Paul in the audience was one of the people. So they came in to service the aircraft. We've changed since then. Regulations changed in the mid-2000s, and we stopped using the military guys for servicing the aircraft. And we now use type certificated organisations who have the engineers to do it. And what happens is the contracts are based on 5-year blocks. It's put out to tender. We have had companies in the UK do it, but at the last round, 2 organisations in Canada won the contract. To be fair, there's an awful lot of experience in Canada using the Twin Otter and the Dash 7, and that's where the contracts were placed, and they provide the engineers to support the aircraft south. So it takes Dash 7 about 8 days to go from Toronto down to Punta Arenas and Rothera, and it takes the Twin Otters about 11 days to go from Calgary, where the organisation is based, down to.
So how would you cope with the loss of an engine on the flight from Punta Arenas to Antarctica?
Well, if you're in the Twin Otter, you're in your immersion suit, and you've got a dinghy, and you look for a ship. There's no way around it. That is one of the most dangerous parts of our operation. When they take off from Punta Arenas, they're at £17,500, which is with the fuel, so it's way over normal weights. We're talking an aircraft that in normal world is certificated at £12,500, not 17,500. So we would try and reduce the weight of the aircraft, so we don't normally use the full permit to fly of 17,500. Most of the time we transit from North America. There's a leg between Guayaquil in Ecuador and Arica in northern Chile, and another leg from Panama to Guayaquil are our longest legs. We probably are only up around £16,500 for those legs, because we have a fatigue penalty for the £14,000 STC, so it's in our own interest to try and, apart from a safety angle, the fatigue penalty makes us think about how heavy we're going to fly the aircraft next time.
Starting off at that sort of weight from Punta Arenas, presumably your altitude capability is severely limited, and on a single engine you're going to be coming down fairly quickly.
One of the reasons we chose the £14,000 cut-off for our routine flying in Antarctica and anywhere else, and the reason we applied for that at the STC, that's the single engine critical weight. So on your critical engine you can still maintain altitude if it's, it doesn't have to be a perfect donkey, but it has to be reasonable, and we do C of A air tests. I know they're not mandated anymore, but we do look at the performance of all our aircraft before they go south, and the engine performance on each engine as single engine. So we do ensure that our aircraft can perform at those, but there's no getting away from it. If you lose your engines at certain points in the flights, both for the Dash 7 and the Twin Otters, you're going to end up doing
I guess the Twin Otter and the Dash 7, they're getting a bit long in the tooth.
Yeah.
So have you got any thoughts about replacement?
We do relatively small number of hours, so the wing life on the Twin Otters is about 33,000 hours, and the fuselage is 66,000 hours. We're doing 600 hours a year. Most of the airframes are only around 10,000 hours, 16,000 hours. We have this fatigue penalty, which has taken a big bite out of our fuselage and wing life. The wing life is, we pay the penalty of about 1.9 to 1 on historical stuff, and now we've got the load sensors in the aircraft, and we actually put that against the actual weights we take off at, and on average now we're down around 1.3 to 1 as a penalty on that 600-ish hours a year. So there are modifications out there. There are 2 mods for the wings. You can either send them back to an organisation called R.W. Martin and they'll relife them, or you can do a mod from another company, which is a 600-hour inspection thereafter to look at the fatigue of the wings. So there are the support issues behind screw jack actuators for the flaps, things like that. There are key components which we are hitting problems with on the Dash 7. The Twin Otters, there's still 600 of them flying. So the Twin Otters, they're remanufacturing the 400 series. The Twin Otter's less of an issue for us. The Dash 7, because it's a bush aircraft used all around the world, but the Dash 7, 4-engine, short takeoff landing, nobody else is using it except the UN and the US military and Air Greenland. For the same reason we use it, they've got some short runways that they are limited at. So there's very few people operate the Dash 7, and that will be the aircraft. And unfortunately, that's our pinch point. We only have one of them. So, looking long term, the C-130J can get into our runway. The H can't, but the 130J can use the Rothera runway. But that's a massive cost compared to operating the Dash 7. So that we think we've got till 2025. With the aircraft reasonably, we've upgraded the avionics, spares packages, stuff like that. So there's a reasonable time out there, but like I say, Dash 7 won't go forever. So yeah, I don't know what the answer is, but yeah, it'll be very expensive if we have to use a HERC.
Okay, and one final question.
It's kind of a follow-on to the last one. Have you tried leaning on any of the RAF logistics people to give you the odd hand?
Absolutely. Well, we did. Normally it's a conversation with the pilot, because the pilot is dead keen. The pilot, they all want to, operate in Antarctica. They do flights to South Georgia. They'd love to. It's about the same distance to come to us. The senior guys in the military, you can quite understand it. The function there in the Falkland Islands is not to come and support us. The function is to support the defence of the Falkland Islands. So this year we programmed in a flight via HERC from the RAF down to Rothera to do an airdrop of drones. And it was really a trial process, and it was done at a weight where they wouldn't need to refuel. So yes, it's on the table, and the limitation on that was because the aircraft overlap and they don't want an unserviceability issue with the aircraft that's meant to be looking after the Falkland Islands. When they overlap the aircraft, when they move them between UK and Falklands, they were going to, when they've got 2 or 3 of the aircraft, they use one of them to do this airdrop, and it's just the timing at the minute, because we have to have the weather window in Antarctica for them to do it. So yeah, it's been talked about, and it was on the table for this year. Whether it will happen this year to weather and all the rest of it, I don't know, but yeah, we are looking at it, and also the Australians are looking at using HERCs as well. They've had a huge injection of cash, and they're wondering whether they move towards the HERC, because they had an Airbus 319 going into a blue ice runway on the other side of the continent, and then they would shuttle out from that airfield using CASA 212s. But it didn't really work very well for them, so they're wondering whether they put skis on the 130J and go that way, because of course the H's are the only one approved with skis, and that's getting very long in the tooth and used by the US National Guard. So there are five, maybe 6 of those. But that's it.
Okay, thank you, Rod. I shall now pass on to my colleague Shambat to propose the vote of thanks.
Yeah, okay, thank you. My name is Shumit. I'm the Secretary of the Bristol branch, and I'd just like to say a couple of words in thanks in response to what you said. So I just thought I'd highlight a few things that stood out as we were talking, really. Just, first of all, I work for Airbus, so it's a very transnational company. And what you were saying is a completely multinational endeavour to firstly get the job done, science. You've got the politics representing each of your nations in a good way, hopefully, and also helping each other out with the safety and the danger aspect of what's going on. Like you're saying, you perform medical evacuation, search and rescue for other countries. So it's not really your job, but if you were in trouble, I'm sure you would like them to come help you as well. And one point you said was, even in a tent, you have 2 pilots, because in case one guy sort of gets carbon monoxide poisoning. I was just thinking, really, when did I hear that before? And I realised that I think last year, there was a case in the UK where a family, several members of the family died in a tent. They were just camping, and because they took their barbecue set. And I think either some or several members of the family died, and that was in the English countryside. And you think, if that would happen, well, there's no one else around for hundreds and hundreds of miles, what would happen? So it highlights the need for sort of to help each other out and make sure things are going correctly. So it's pretty good to know, and the people you hire must be of that caliber. They wouldn't just go, yeah, whatever. They want to help, and they'd be that sort of natured people. Another point that stood out was that the extreme operations of what you do. So sitting in Bristol Airport yesterday morning about 5 a.m. I was waiting for the flight as they cleared the runway of snow, and moaning, and they had to get the de-icer truck out to clean all the aircraft, and thinking, okay, right, but what you're saying must be 100 times worse than you have to clear the runway of snow every morning at -30 and try and de-ice it. You didn't really mention about this.
No, we don't actually de-ice the aircraft. They're painted black. we'll sweep the snow off the wings, and then we'll let the sunlight do the work, and if you've got a nice sunny day, it'll de-ice the aircraft for you.
Wow.
So yeah, we don't use de-ice.
Okay. We have to wait a bit, I reckon.
Yeah. Time's on our side.
Yeah. That's quite important. So again, the technical aspect of if we had an Airbus aircraft, we'd be doing cold weather trials. We'd send our aircraft out to Arctic or something and sit there in the polar region or something and give heated fuel to make sure it doesn't freeze up. But I don't know how you deal with that sort of thing.
No, we just pump the fuel out the drums into it, and
it doesn't freeze.
No.
Oh.
I mean the medevac that they did at the pole. I know they used Twin Otters on that flight, not the Hercs, because of the hydraulic systems. They were about -70. They were going to experience at the pole. So the Twin Otters are very basic hydraulic system. It was basically your flaps and your brakes. So yeah, and the steering. Well, you don't particularly need the steering. You're not limited to a runway that's only 30 metres wide. You've got wherever you want. So if it fails, you turn into a little pole will be as live as you want it.
Right.
So, and as long as you want to stop.
As long as you need it, keep going. Just one other point is the scientific aspect that you were saying was, we've managed, you said carbon dioxide particles and parts per million is about 30 parts per million over the last 1,000 years, and now in the last 17 years we've managed to rack up the same amount. So it's a measure of responsibility on all of us really, just to say that, okay, what can we do ourselves to try and improve the environment? It's not all nonsense. It's the fact of piling up really to say that we're damaging the earth, and also those of us in positions that we can do something about to encourage our companies and the groups and things that are producing vehicles and engines and fuels to try and make sure that responsibility is passed on to meet those greenhouse targets and those environmental targets when they are there. So I think it's something to be mindful of. And the point at the end really, the kind of a difference of 10 degrees at the Antarctic is the difference between the Ice Age and today. 10 degrees, it's nothing, it's like between today and summer, it's like when Brittany is in fact. It's like curious, the life is fragile. 10 degrees, it's not that much. So, be respectful to the world and be respectful to ourselves. But yeah, thank you very much for that interesting talk. Thank you.